Okay, so welcome. Our speaker today is Karen Collins, an alumna of this esteemed educational institution. She did her bachelor's degree at Georgia Tech in engineering, electrical, and then worked in industry for a while, and then retired. And in her retirement decided to do astronomy, so she came here. She did her master's degree with Carol Grady and me on protoplanetary disks, and her PhD with John Kielkopf on exoplanets, and then had a postdoc at Vanderbilt and a postdoc at Harvard, which she's still doing, all from the comfort of this metropolitan area. And she's going to talk to us today about exoplanets, the TESS mission in particular. So thank you very much for coming back. Welcome back. Thank you. Good to be back. One of our first PhDs since the resurrection.
Thank you, Jerry. I do work for the Center of Astrophysics in Cambridge, Mass. Although I do most of my work from my office here in Louisville, through the very kindness of my boss, David Latham, to allow that setup, and it's appreciated every single day when I get out here. We are involved in the TESS mission there, and I want to tell you today about the history of transiting exoplanet science, the goals of the TESS mission, the current status, and some of the results that we have so far. Just got to put my advertisements up there here. All of this is made possible by NASA and the entire worldwide team of TESS and TFOP members that we have to do the follow-up work for TESS, and I'll show you what that means as part of the presentation. I've gotten some good content from Deanna Dragomir, Natalia Guerrero, and Sarah Seeger from MIT in this presentation, so I want to throw out a thank you to them too. Okay, let's start with some history, see how we got here. We first need to understand two of the exoplanet detection techniques, and there are many others, but these are the two that are primarily used as part of the TESS mission. The first is called the transit method, and as the planet moves in front of the star, it causes the star to dim slightly, and that dimming is proportional squared to the radius of the planet, to the radius of the star. So we learn the radius of the planet relative to the radius of the star, and then we have other techniques to understand the radius of the star itself, and thus we can get a physical radius of the planet. So similarly, the radial velocity technique lets us measure the mass of a planet and uses hopefully your friend the Doppler effect to detect the reddening and bluing of the light spectrum as the planet orbits the star. It tugs on the star and causes the star to move, and then we can see that in the spectrum of light as the spectrum of light moves back and forth. So these are the two key methods. Once we know the radius and the mass of the planet, we know the bulk density, and we can learn lots more from there. Okay, this all started back in the mid-2000s with several ground-based surveys. You can see that these are not large telescopes. Look at the EXO project there in the top left. This was led by a collaborator of John Kielkopf's. He actually brought him here during my program, and we had a great chat. We've become good friends. He's on the TESS mission too, and thank you, John, for that connection. There were 6 or 7 exoplanets discovered, some of the first exoplanets discovered. Then surely you've heard of HAPNet planets and WASP planets, if you've read any popular science. And then near and dear to my heart is the Kelt North and Kelt South survey. It worked out kind of strangely that Jerry brought a person he heard on the radio
Car
from
Talk.
Vanderbilt up here, Car Talk, brought him here to do a talk and got us connected with the KELT survey, which was being run out of the Ohio State University and Vanderbilt University at the time. And Josh Kepler is still a great collaborator. So with that team, Dr. Kilcoff and I have worked on the discoveries of 25 hot Jupiter type exoplanets. And then there are the newer breeds, South, more sophisticated, and NGTS is a real late addition to the mix, and they are now repurposing their instrumentation to help follow up TESS planets as opposed to trying to search for new planets. Then things moved to space in about 2006 with the Kourou Space Telescope. This is a European mission. That team discovered about 30 planets, which includes the first super-Earth. That one was about 2 times the radius of Earth, that planet. That operated up until 2013. Then the NASA Kepler mission came along in 2009, and this mission ended up being divided into 2 different chunks. The primary Kepler mission, it stared at one spot in space for 3.5 years and didn't look around at different fields or anything, stared at this one place for the prime intent to find long period Earth-like planets. It did do that. It found more than 2,300 planets so far, and there are still 2,400 more planets that still need confirmation. So work is still going on every day with the Kepler data. All of this data is public. Go get it. Do your own thing with it. The downside of Kepler is that the stars are far away, relatively far away, and therefore dim, and we require relatively bright stars to do radial velocity measurements, so a lot of them do not have masses. 3.5 years into the mission, the second of the gyroscopes broke, and the telescope could no longer point in 3-dimensional space. So ingeniously, an idea came around to point it at the ecliptic plane and let the solar wind help guide it in one dimension, and you still had the 2 flywheels in the other dimension, and there's a little bit of thruster help for that too. So that continued to operate then until 2018 with hundreds more planet discoveries. Okay, I'm going to try to get you oriented with this graph here first. It's going to zoom out, and what you're going to see is where you see a blue dot, that is a non-Kepler planet, like the ground-based planets that were discovered by around 2015, compared to the Kepler planets, and the Kepler planets show in gray dots. So there's 10 light years. We're zooming out away, so 20 light years, 40 light years. You see some ground-based planets coming in, 100 light years away, 200. You start to see some sprinkles of the Kepler planets coming in, but now you see the density building out to 2,000 and beyond, all the way out beyond 4,000 light years away. So they become very dim, and at least with today's technology, impossible to get precise radial velocity measurements of them. So how do we fix this problem? Introducing the Transiting Exoplanet Survey Satellite, TESS. My favorite Darth Vader-like entrance for TESS. So the idea of the Transiting Exoplanet Survey Satellite is to survey nearly the entire sky, looking for exoplanets around nearby bright stars. That's the key, nearby and bright stars. The main science goal is to measure the masses of 50 of those planets that have a radius of less than 4 Earth. Now that's interesting because TESS itself is a transit science instrument, and you can't measure masses with that. So the point is we have a huge ground-based team to help us measure the masses of the planets that, the planet candidates that TESS discovers. Now luckily, John and I both got to go down to Kennedy Space Center to watch the launch of the satellite. Unfortunately, it didn't go off on the day it was supposed to go off.
TESS will find thousands of new planets.
I don't know where that came from. The point is, we came back. John had commitments. We learned that it was going to launch the next day, so I turned around and went back down there and did get to see it. But John unfortunately had to stay here. But if you ever have a chance to go see a rocket launch, please do that if you haven't done it. It's amazing and a great trip. The Kennedy Space Center is an awesome place to visit too. Okay. One thing that I find fascinating about TESS is its launch and its unique orbit compared to some of the other satellites. And I can try to explain it, but I think it's best to watch this video so that you can see the path and then how the final orbit appears. You're going to see the Earth in the center and the Moon orbiting around the Earth, as well as the satellite.
TESS will find thousands of new planets orbiting nearby stars. To accomplish this,